Usually when we look at the systems running our homes, there is this expectation of just surface level simplicity. Like you flip a switch, the lights come on,
Right.
you turn a sleek, modern shower handle, and perfectly mixed warm water just flows out. I mean, we really like things to be hidden away, functioning essentially like magic.
We absolutely do. I mean, we appreciate the convenience of that modern aesthetic, right?
Sure.
But we actively ignore the complex geometry, the fluid dynamics,
Yeah.
the metallurgy, all of it hiding just, half an inch behind the drywall.
Oh, for sure. But then, you decide to tackle a home improvement project yourself.
Yeah.
You step into the world of DIY plumbing, you open up that wall, and suddenly that whole illusion of simplicity just completely shatters.
Oh, yeah, it's gone.
Right. You are staring into this dark, wet cavity of jagged pipes, and you realize you have absolutely no idea how any of these systems actually interact.
It is the absolute definition of jumping into the deep end.
Yeah.
You're dealing with pressurized water inside a wall. I mean, the stakes are incredibly high, which is why having a precise roadmap is it's critical.
And that is exactly what we are providing for you on this deep dive today. Our mission is to demystify a highly practical but surprisingly intricate DIY project. We're analyzing the transition from an old, clunky, three-handle tub and shower faucet.
The ones everyone hates.
Exactly, the worst ones. Transitioning from that into a sleek, modern single-handle Moen valve.
Upgrading to a single-handle pressure-balanced valve, it's a massive functional upgrade for any bathroom. It regulates temperature fluctuations automatically. But the journey to actually get that beautiful piece of hardware installed, it is full of hidden traps that can easily, turn a weekend project into a complete disaster.
Oh, absolutely. And we are drawing our insights today from a fantastic, just highly detailed instructional video from the YouTube channel, How to Plumbing. It is essentially a masterclass, really, just packed with invaluable, hard-won tricks of the trade. The creator really focuses on the nuances of the installation.
They really do.
Yeah.
It's not simply about, connecting pipe A to pipe B. The source material is basically a study in anticipating physical limitations and spatial constraints before they become actual emergencies.
Right. So before we can stand under the luxurious rainfall of a modern single-handle valve, we have to surgically remove the ghosts of plumbing past.
Yes, the tear out.
Yeah, and we have to do it without destroying the bathroom tile, which is terrifying. Where do we even begin with tearing out an old three-handle setup?
Well, first and foremost, you turn the water off to the house.
Okay, yeah.
Then you double check it. You verify the water is actually off by opening a faucet at the lowest point in the house.
I would assume that is entirely non-negotiable.
Oh, completely non-negotiable. Do not skip that. So once the system is actually depressurized, you are dealing with an old valve assembly that consists of 3 separate stems. Right. You've got one for hot water on the left, one for cold on the right, and then one right in the middle.
The diverter, right.
Exactly. That middle stem is the diverter, which dictates whether the water travels up to the shower head or, down to the tub spout. So you start by stripping all the exterior hardware. Just take off the handles, remove those decorative plates, which in the trade we call escutcheons, and unscrew the sleeves.
Okay, so the video shows the plumber using these highly specific, like elongated sockets to get the actual stems out of the wall. I mean, my instinct as a DIYer would normally be to just grab a trusty adjustable wrench, but it looks like that wouldn't even reach.
Oh, an adjustable wrench won't do you any good here at all.
Really?
Yeah, the brass nuts holding those stems in place are recessed deep inside the wall cavity. I mean, they're often completely surrounded by tile and plaster. You can't get standard jaws in there. You need specialized shower valve socket wrenches.
Oh, okay.
They are hollow and extra long, which allows them to slide all the way over the stem and actually lock onto that recessed nut. So you unthread the hot and cold stems, and then you pull out the seats.
The seats?
Yeah, those are the little brass rings inside the valve body that the stems physically compress against to actually stop the water flow.
Got it. Now, there's a very specific pro tip in the source material right here regarding that third handle in the middle, the diverter. The plumber explicitly says to leave the old shower diverter stem fully in place until the new valve is actually installed.
Yes, that is a huge tip.
But my instinct would be to just, rip everything out to clear the workspace. Why on earth would you leave a piece of the old system lingering in the wall?
Well, if you think about the physics of what is happening behind the wall, you have this heavy brass block attached to old, potentially very brittle copper pipes.
Right.
If you remove all 3 stems at once, you have nothing holding that heavy brass body steady. Leaving that middle diverter stem in place acts as a Well, a physical reference point, but mostly a structural anchor.
Oh, so it keeps it from just flopping around.
Exactly. It helps keep the entire old valve assembly somewhat stable while
Huh.
you are working around it, cutting pipes, prepping the
Yeah.
space. You definitely don't want the old valve dropping down into the wall cavity or stressing the remaining pipe joints before you're actually ready to pull it out.
Okay, that makes perfect sense. You are basically using the old hardware as a temporary scaffolding.
Precisely.
But thinking about the visual footprint of this project, I am seeing a massive discrepancy. Like, we are taking out three separate handles that span maybe 8 or 10 inches across the shower wall,
Right.
and we are replacing them with one single handle right in the center. I mean, wait, aren't we going to be left with giant, ugly, gaping holes on the left and right where the hot and cold handles used to be? How do we fix that without completely retiling the shower?
Yeah, that aesthetic fear is exactly why so many homeowners just hire out this job. It looks impossible to fix cleanly. But modern plumbing kits have engineered a pretty brilliant workaround. You actually don't have to replace a single tile.
Really, no tile work at all.
None. The solution is a specialized component called a repair plate. Or, sometimes you'll hear it called a remodel plate or a Smitty plate in the trade.
Okay, but how exactly does a metal plate fix two gaping holes in a completely waterproof surface?
So when you source your new single-handle Moen valve, you can purchase it with an oversized, elongated metal trim plate. It's specifically dimensioned to cover the wide footprint of an old 2- or 3-handle system. But, and this is key to utilize it properly, you have to be incredibly strategic about how you create the access point in the wall.
Ah, and the new valve kit comes with a plastic template for exactly this reason, right? It maps out the exact size of the access hole you need to cut.
Yes, it takes the guesswork out. And in the source video we are analyzing, the wall they are dealing with it's essentially a fortress.
Yeah, it looked intense.
It is not modern, easily cut drywall. It is an old-school plaster wall, backed by solid concrete, reinforced with heavy metal wire mesh, and then finished with ceramic tile.
So you definitely can't just take a hammer to it and hope for the best.
If you fracture the tile beyond the footprint of that template, the repair plate won't cover it, and water will infiltrate your wall and rot the framing. The pro strategy here is to tape that Moen template directly to the tile, perfectly centered over the old middle diverter valve.
Right.
Then you start breaking the material right in the dead center of the template opening, and you painstakingly work your way outward toward the edges. You are trying to preserve as much of the surrounding wall structure as physically possible.
I see. Because the integrity of that surrounding tile is what actually seals the deal later.
Precisely. You are creating a surgical access window. Later on, that oversized repair plate will mount to a hidden backing bracket positioned behind the wall. When you tighten the screws, it clamps the exterior plate and the interior bracket together in a sort of sandwich style against the tile you preserved.
Oh, wow.
Yeah, it seamlessly covers your surgical center cut and the old outer handle holes, creating a watertight mechanical seal.
That is so smart. Okay, so the wall is open, the surgical window is prepped, the old clunky brass valve has been severed from the pipes and removed. Now I'm ready to slide the shiny new Moen valve into place, grab my blowtorch, and start melting some metal to connect the pipes. Right.
Oh, absolutely not. If you apply a torch to that valve right out of the box, you will destroy the entire project before you even finish the first joint.
Wait, what am I missing? The valve body is solid brass. Brass can handle heat.
The brass body is only the housing. We are moving into the absolute golden rule of modern plumbing installation here. Before you even think about lighting a torch, you must remove the cartridge from the interior of the new valve body.
The cartridge is that plastic cylinder sticking out of the middle of the brass block, right?
Correct. The cartridge is the actual brain of the plumbing operation. It is a highly engineered piece of plastic that controls the complex mixing of hot and cold water when you rotate the handle. And to do that without leaking, it relies on several tiny, highly sensitive rubber O-rings and internal seals.
Okay, let me make sure I understand the physics here. So, soldering the copper pipes connected to the brass block while that plastic cartridge is still inside is essentially like leaving your smartphone on the dashboard of a car in the middle of summer. I mean, you're just going to completely melt the sensitive internals, right?
That is the exact mechanism of failure, yes. Brass has incredible thermal conductivity. The extreme heat from your torch travels through the metal housing almost instantaneously. If that engineered plastic cartridge is sitting inside, those crucial rubber seals will warp, melt, and completely lose their structural integrity.
Which means the second you turn the house water back on, you have pressurized water flooding out from the inside of your brand new valve.
Immediate catastrophic leaks.
Yeah.
And a ruined cartridge that requires a very frustrating trip back to the plumbing supply store.
Yeah, we definitely want to save the cartridge. What is the actual process for safely extracting it from a brand new valve?
It's simple, but delicate. The top of the brass valve housing, there is a small metal retaining clip. You grab that clip with a pair of pliers and pull it straight up and out.
Huh.
Then you take a flathead screwdriver and gently, very gently, pry the plastic cartridge loose from the brass body.
Okay.
You remove it entirely and set it somewhere far, far away from the heat zone.
And the source video highlights a really subtle detail right at this step. They explicitly say to mark the hot and cold sides of the brass valve body with a marker before you set it aside.
Yes, that is a lifesaver. Once the cartridge is out, the brass block is virtually symmetrical. If you lose track of the orientation and solder it in backward, your hot water will be cold and your cold water will be hot.
Oh man, that would be terrible.
It is a classic rookie error that requires cutting the entire assembly out to fix.
Yikes. So pull the clip, pry out the cartridge, mark the orientation, and then the video shows the plumber using a small wire brush inside the hollow brass chamber.
Yeah, you are prepping the empty brass valve body. By running a wire-fitting brush inside the chamber, you are removing any microscopic manufacturing debris, oils, or little burrs of metal. You want that interior brass to be perfectly smooth so that when you eventually slide that delicate cartridge back in, those rubber seals glide perfectly into place without snagging or tearing.
Makes sense. Okay, so the sensitive plastics are secure, the brass housing is prepped. Now we arrive at the actual puzzle, connecting the old copper water lines hidden deep inside the wall to this new valve. And watching the footage, this just looks entirely claustrophobic. You are working in a tiny, dark 3-inch gap between jagged tiles and concrete.
It is a high-stakes copper puzzle in extremely tight quarters. The initial hurdle is simply cutting the old pipes down to the correct height. You absolutely cannot fit a standard pipe cutter in there, and you certainly don't have the stroke clearance to use a hacksaw inside a 3-inch surgical window.
Yeah, the plumber pulls out a specialized tool specifically for this space constraint.
The mini tube cutter. It is indispensable for retrofits. It's a very compact wheel-shaped tool. You basically clamp it onto the copper pipe, tighten it slightly, and rotate it around the pipe in the tight space.
Oh, so you don't need to swing a handle.
Exactly. After every rotation, you tighten it a fraction of a millimeter more. It slowly scores and cuts through the copper wall cleanly without requiring the swing clearance of larger tools.
Nice. So once we have cleanly cut the old hot and cold lines, we have to bridge the vertical gap between those old pipes and the new valve housing. The video runs through a specific array of copper fittings used to reconstruct this connection. They mention half-inch copper couplings, 45-degree angles, 90-degree angles, and then they place a huge emphasis on a component called a street 90.
Ah, yes. The Street 90.
I think most of us know what a standard 90-degree pipe elbow looks like. It's just a little metal macaroni noodle. But what exactly makes it a street 90?
This is where we really get into the spatial engineering of plumbing under tight constraints. So a standard 90-degree elbow has what we call hubs on both ends. Yeah, a hub is basically an expanded collar. It is slightly wider than a standard half-inch pipe, so the regular straight pipe slides inside the fitting on both ends.
Oh, I see. The standard fitting acts like a sleeve that slides over the straight pipes.
Exactly. But a street 90, or street elbow, is fundamentally different. It has a hub on one end, but the opposite end is the exact outer diameter of a standard straight pipe. It has no hub on that side.
Wait, why does lacking a hub on one side matter so much in this scenario?
Because that non-hub end is designed to slide directly inside another standard fitting, or in this case, directly inside the hub of the new shower valve housing itself.
Oh, I see the geometry now. With standard fittings, you would need the valve housing, then a tiny 1-inch piece of straight pipe, and then the elbow fitting to connect them all. The street elbow just plugs right into the valve directly.
You got it.
Okay.
It completely eliminates the middleman pipe segment. By nesting the fittings directly into each other, you are saving precious fractions of an inch behind the wall. It yields a much tighter, cleaner, and more compact plumbing layout.
Yeah.
And when you are forced to work through a tiny template hole in a thick plaster bunker, managing those dimensions is literally the difference between success and failure.
It really is just structural Tetris.
It really is.
But, piecing the puzzle together perfectly isn't enough, right? We have these perfectly aligned, clean-cut copper pipes wedged together, but metal on metal isn't inherently watertight. Water under pressure will find even a microscopic gap. How do we actually fuse them seamlessly?
Well, that brings us to the chemistry and physics of soldering, or what plumbers call sweating the joints. And the vast majority of plumbing failures occur right here, mostly because of inadequate surface preparation.
Yeah, the video dives deep into the prep process. And one detail stood out to me immediately. Usually you see DIYers using that rough emery cloth or standard sandpaper to shine up the ends of the copper pipes. But the plumber, in our source material, uses a product called fiberglass mesh. Visually, it looks exactly like the mesh from a window screen.
Sandpaper is common, sure, but fiberglass mesh is the professional standard for a few critical reasons.
Why abandon standard sandpaper?
First off, standard sandpaper sheds. It leaves behind the sandy, abrasive grit that can easily contaminate the joint and actually prevent a perfect seal. Fiberglass mesh does not shed.
Oh, that makes sense.
Secondly, the abrasive matrix cuts right through greasy grime and heavy oxidation on old pipes much faster than standard paper. And third, it is completely reusable. You can use a single strip of that mesh on a dozen fittings, rinse the debris out, and use it again.
Wow, that's incredibly efficient.
It is. You are shining up the outside of the pipes with the mesh, and you are using a wire-fitting brush to shine up the inside of the hubs. You must have bright, shiny, virgin copper everywhere solder is intended to flow.
Right, virgin copper. Once everything is stripped down to that shiny state, the next component is the flux. Now, for the uninitiated, flux is a paste you brush onto the raw copper right before you press the pieces together.
Correct.
The source specifically recommends a brand called No Corrode Flux, and they emphasize stirring it aggressively before application. What is the actual chemical purpose of this paste?
Understanding flux really requires understanding what happens when you heat metal.
Yeah.
You aren't just melting solder over the outside of the pipe like a hot glue gun. You are relying on a fluid dynamics principle called capillary action.
Capillary action. Okay, is that similar to how a sponge absorbs water against the force of gravity? Or like how tree roots pull water upward?
Exactly the same physical principle. When you heat the copper joint adequately and touch the wire solder to the edge of the fitting, the solder liquefies. It actually defies gravity and actively sucks itself deep into the microscopic gap between the fitting and the pipe, wrapping entirely around the circumference.
That's amazing.
But, and this is a big C, but capillary action absolutely requires the copper to be perfectly clean and free of any oxidation.
I would assume applying a 1,000-degree blowtorch to copper instantly causes aggressive oxidation.
It does. The moment oxygen hits heated copper, a barrier of oxidation forms, and the liquid solder will just refuse to flow into the joint. It'll bead up and fall off.
Ah, so the flux.
The flux is a sacrificial chemical paste. It coats the copper, shielding it from the ambient air while it heats up. As the metal reaches soldering temperature, the flux chemically etches the metal one last time and burns off impurities, drawing the liquid solder deep into the joint for a completely watertight molecular seal.
So stirring the paste just ensures the active chemical agents are perfectly distributed before you paint it on. I just love knowing the exact mechanism behind the rule. Okay, so we have our shiny pipes coated in chemically active flux, and we begin assembling the pieces for a dry fit before firing the torch. And I noticed a brilliant, very subtle physical manipulation from the video right at this stage.
No, the tapping trick.
Yes, when you stack all these greased up copper components together, they naturally want to just slide apart.
They absolutely will slip. I mean, you will spend 10 minutes getting the valves perfectly leveled and aligned. You'll turn your back to ignite the torch, and gravity will just pull a fitting completely out of place. It's maddening.
Right. But the plumber combats this by doing something very intentional. As he pushes the Street 90s into the valve housing, he gently but firmly taps the fitting with his tool. He actually notes that doing this sets them snug so they don't untangle and fall out all over the place.
It is a phenomenal trick based on manufacturing tolerances. Copper pipe and fittings are manufactured with a microscopic taper.
Oh, they aren't perfectly straight cylinders.
Nope. By giving the fitting a gentle, solid tap, perhaps with the handle of a screwdriver or your pliers, you are utilizing that taper to friction lock the pieces together. You're temporarily wedging the copper into the brass hub. The entire assembly becomes rigid. You can adjust the whole unit, verify your depth to the tile surface, and guarantee nothing shifts when you finally bring the flame to the metal.
Man, it's those tiny moments of applied friction that save you from recutting an entire assembly. Okay, so you solder everything up, you let the copper completely cool down to room temperature, and then because we strictly follow the golden rule, we go retrieve that delicate engineered plastic cartridge we saved earlier.
The crisis has been averted. You slide the unmelted cartridge back into the cool brass housing, and you push the metal retaining clip back down to permanently lock it into place.
Beautiful.
From there, it is purely cosmetic assembly. You mount the backing bracket, you screw down that oversized decorative repair plate to sandwich the tile, and you slide on the shiny new Moen escutcheon. The surgical access hole is officially sealed.
We are in the absolute home stretch. We just have to attach the actual single handle, the piece you physically manipulate to turn the shower on. And here we meet the final boss of DIY frustration, the tiny set screw.
Ah, yes, the infamous Allen screw.
These fasteners are notorious for a reason. It is a microscopic screw hidden up inside the bottom of the handle, and trying to maneuver an Allen key into it while it is pointing straight down at the tub floor, usually in a cramped space, it is infuriating. You almost always end up stripping the head of the screw.
It's the worst. But the source material provides one final, incredibly elegant trick for this exact problem.
How do we bypass the awkward angle?
You simply don't install the handle while the cartridge stem is in the standard straight-down off position.
Wait, really?
Yeah. Before you put the handle on, you grab the brass stem of the cartridge and rotate it 90 degrees to its side, say pointing to the 3 o'clock or 9 o'clock position. Then you slide the handle onto the stem.
Oh, because now the hole for the tiny Allen screw is facing out toward the side wall of the shower enclosure rather than straight down into the cramped tub surface.
Exactly. It provides you with a completely clear line of sight and plenty of rotational room to actually turn the Allen key. You can seat the tool perfectly and tighten it down firmly without any risk of stripping the metal head. Once it is fully secured, you just rotate the handle back down to the bottom off position and the installation is complete.
It is such a simple spatial adjustment, but it removes so much unnecessary frustration.
I love it.
Wow.
Well, let's synthesize this entire journey. We started by staring into a daunting, wall-smashing DIY nightmare. But by analyzing the mechanics, by knowing to pull the cartridge to save the thermal integrity of the seals, by utilizing the Moen template and the clamping force of the repair plate.
The Smitty plate, right.
Or the Smitty plate. And by understanding the space-saving nested geometry of Street 90s and meticulously prepping the metallurgy with fiberglass mesh and sacrificial flux, a terrifying demolition safely transitions into a highly achievable victory. It really proves that these complex systems are manageable. It just requires respecting the physics of the materials and, not rushing past those invisible preparatory steps.
Absolutely. And it leaves me with this final thought for you to mull over. The next time you step into a modern bathroom and effortlessly rotate that single-handle shower valve to find perfectly mixed warm water, take just a moment to look past the shiny chrome exterior.
There's a lot going on back there.
Yeah, picture the complex spatial puzzle of nested copper Street 90s. Envision the perfectly applied chemical flux that pulled liquid solder into microscopic gaps against the force of gravity. And think about the hidden brackets of a repair plate resting just millimeters behind the tile, silently clamping everything together. It really makes you wonder what other intricate, meticulously engineered, invisible systems are silently holding your home together right behind the walls you walk past every single day.
It's a fascinating perspective. There is always a deeper layer of engineering to discover if you just know where to look.
So true. Thanks for joining us on this deep dive. We'll catch you next time.